course, and he went by Chris Cornwell. And he's, I think, if everything I said confuses you, he's going to work through some examples, and he's also thought a lot about the augmentation polynomial, so if you have any questions about it, you can, he has thoughts about it.
Now, as Ekholm, we conclude the lectures taught so far by Lenny about smart contact homology and applications.
Thank you. So my talk will try to say a few words about recent developments and already somehow about the joint project with Lenny and Bafta myself. And so, as you heard Lenny mention a few times, there were some sort of contacts made with physics, and I will try to sort of describe where they come from and a little bit about what they predict, and then somehow try to find geometric sources for these predictions. So first I will start with discussing a little bit of physics, and this physics is mainly not new stuff, so I will take it back to the late 80s, early 90s, and then kind of go towards the more modern predictions and where the relation comes from, and then discuss what are consequences, predictions, maybe I should write bigger, and then and all of this is related to this augmentation polynomial, so I will then discuss first classical augmentations, not contact quality, and then what I would call quantum augmentations. Okay, so but the whole story starts in Chern-Simon's gauge theory, and I want to give just a brief description of that. So we start with a compact gauge group, which is G, and for us it's somehow maybe HUN-REN most often. And we have a free manifold Y. And then if we pick a connection on a G bundle, so then we can form the Chern-Simon's action, which is the following thing, and then somehow there is some question about normalization here, that this is a constant up front, but this is what's common. We take the trace of the A wedge A, and then we add 2/3 of the cube of A. So this is the Chern-Simon's action, and it has a lot of well-known properties, but let me anyway say some words about it. So one of the secrets to this free manifold integral is that it somehow is really a shadow of a four manifold integral. So if X is a four manifold, closed manifold, then if you take and P is, let's say, SUN value over X, then the second Chern you take a 4-manifold bounding your 3-manifold, so if this is y, and then you somehow attach to it x, then and you have this color where they say trivial connection in node up here on a trivial one, and then you change the connection to a node plus, so this is 0, 1 plus t a, then the contribution to the integral from the color is exactly the Chern-Simons hash. So in particular, you find that and if you think about it, if you change the trivialization of the boundary by non-monotonic gauge transformation, that corresponds to changing the C2, if you have some kind of reference, perhaps closing up here. And so we find that some of this large gauge transformation changes this, but changes it in somehow integer way. Okay, but for sort of small gauge transformations, it's invariant, but for large ones it changes. But then let me also point out the next basic thing about that, if you vary the connection a little bit, then the corresponding variation of the Chern-Simons is given by, and I'm probably darking constant at this point, the curvature wedge, the variation. So we find that the variation is 0 if A is flat. This is also basic facts about the Chern-Simons function, so far nothing very fancy. And then the Chern-Simons gauge theory is a physical theory in the way I'm going to describe it, and there's been, of course, a lot of mathematical work making sense of this from a mathematical point of view, but I'm not sort of the right person to try to list more references, and I'm just say that I give them out, and I know that I probably offend many people, anyway, so the Chern-Simons theory is about the Chern-Simons partition function. This partition function is given by a path integral, which is looking like this. So K here is level or something, but it's K sort of like 1 over time constant, if you think about the normal path integrals in physics. So, so the integral is supposed to take place over the space of all connections, and that's somehow the standard infinite-dimensional space, and you can define the pressure and so on and so forth. And so it's somehow always a science to try to make sense out of this type of integrals, but recipes were developed and it goes back way before this. And in particular, there is somehow a Feynman calculus for such integrals, which I'm not going to review, but I'm going to use a little bit about it. So Feynman calculus gives the perturbation expansion of this thing in terms of 1 over k. So in other words, if we to somehow fix a flat connection and try to make sense out of what this is when you take one of k small, then you can get the perturbation expansion for this thing. And the point why this is spoken about here is that the coefficient, so the coefficients in this expansion will be topological invariance of 1. Given that it makes sense of this, it's the only thing it can depend on, right? This is y itself. So, and again, I'm going to borrow some statements from this standard facts about finite diagrams and so on, but at least, so I wanted to lead up to one picture, so you have to, I remember from some kind of physics class or recall, but the point with these diagrams, finite diagrams, it's the diagrams with R loops contribute to 1 over k to the power of r. So that's where the coefficients come from. So 1 over k, maybe I put a coefficient. Which is for us a function of n. So where we took g was, let's see. So that's somehow what we should expect here. Let's take a look at, so take a look at this somehow extremely brief view peek into the world of finite diagrams. So the interaction term, so let's say somehow this cubic term in here, so remember that was right here, is given by, so it is this cubic term, right? So it's Aij, which k, which aki. So this is just matrix multiplication of these two, and another matrix multiplication. But then remember, we take the trace in the action. Right? So this is somehow what it looks like if you write it up in local coordinates, or it's given trivialization. Now, to such vertex, if you're doing Feynman calculus, there is some sort of diagram like this associated, and we put propagators on the lines and we put something at the vertex. But it's not so important for us right now. But we can somehow try to count how many such diagrams there are. And a convenient way to do that is so remember there are, since we're working in this SUN, there are somehow n gauge indices, right? So the n by n indices. And so what one can do is you can take this graph and you can fatten it up. Okay, maybe I just at the top. And you can see that at this, so you're assuming this j index, k index, and I index. So you can sort of write a, I, j, k. And so if you have a more complicated final diagram, so I don't know, maybe this one. To do this fantasy, I should probably do it in some color. So you get a little surface sitting on place, and then here the way that you color these things, of course, propagate over the surface. Right? So you find that, and since there are n gauge indices, you see that if you're summing over the gauge indices, you would get a term proportional to n to the power of h, where h is the number this is the number of, I think I used H. H is the number of boundary components in what is called the fat graph. Now, so the coefficients here, somehow we have the coefficients of n to the power h over k to the power r. So r is topological invariance. And what I'm saying right now is taken from some written paper from 92. It's called Chern-Simon's theory and something about so we can also express this in terms of the genus of the Riemann of the surface that it was. So the genus is, this is of course simple, it's just R loops minus poles plus 1 over 2. And so we can somehow reorder the thing and write this up in the following way. So we write this partition function, so I'm changing notation, calling this now gamma in change, gh of y. I'm going to write it up as something like this. So I have numbers, depending on genus, the number of boundary components, n to the power h, and then kappa, which is some related to k, and n to the power 2g minus 2 plus h. This is just rewriting where kappa is equal to 2 pi k plus 2. This is a sort of standard thing.
What is this n to the h number?
N to the h? So now we're looking at the contribution from such fat diagrams with h boundary components. And since if we sum up the gauge indices, there are n of them, we'll get a factor n to the power h that somehow magically sits in such sums, right? Okay. So I mean, if you draw one such diagram, so you have, for each boundary component, you have sort of n choices. It's kind of natural to call this coefficient out of such. That's what I'm saying. Okay. And we rewrite it further. So I'm still going to stop these exercises, but not quite yet. So. Lambda to the 2g minus 2 plus h, where lambda is slightly different, so lambda is equal to kappa times 2. So this is the end of this. This is just algebraic. So now, what one is somehow tempted to do, and what we actually did, is that when you look at this thing and you have some experience with this, you see that this looks like some kind of expansion of a partition function for a string theory, because you somehow recognize that this should be the genus and this should be the number of boundary components. So, in fact, and I want to say something about that, but I think I'll skip details. So there is what's called an A model. So this also A model. Of Roman space. maybe I'll just say one word of what this is. So what we are looking at, we're looking at maps. So maps phi from a Riemann surface with boundary into T star y, and the boundary on boundary they're mapping into y. So this is somehow like the homomorphic curves in first degree. But we have some, so there's some of the fields of the theory, so this is some nonlinear signal models as well, but looking at such maps, and over these maps there are two sections of vector bundle. So there is a section psi and another section psi, slightly different bundle. Just as it is. So let me sort of stop this. I won't have time to explain very much more. But so there, in terms of these fields, you somehow write up an action, which is you can show gives and with this action you write down a path integral against which integrates over all such maps and integrates also over all such fields. And then you would want to kind of define a partition function of that theory. And at this point, with such theory, there are two things. So one is that you can actually show, because it's somehow invariant, that the theory, in this case, we have cotangent on the free manifold, localizes. So the only contribution to this path integral comes from actually homomorphic maps. So you're supposed to count homomorphic maps. And so this partition function of this theory can actually be reformulated as a partition function as an integral over the moduli space of holomorphic maps. So so this sort of string partition function turns out to be equal to, let's say, an integral of the moduli space of holomorphic maps, and with boundary y, like this, and then in this particular case, there are no homomorphic maps. We all know that if you take boundary condition,
What's the action?
It's an I plan to write it, but I can tell you later. I think it's better because I won't get anywhere if I start with this. But the action is not, it's not difficult. It involves the fields. It's something like this. And, okay. But let me know. Okay. So this reduces to an integral over the moduli space of homomorphic maps. But as you know, in this situation, there are absolutely no homomorphic maps with boundary on the zero section, except for the constant maps. So we have the constant maps. And so, if you want to write this integral, you have to take into account perturbations of constant maps. And then Witten goes on and he defines in some other paper something he calls string field theory, which is an extremely nice invention. But for this string field theory, you can now somehow just identify the perturbation theory for this theory with the perturbation theory in Chern-Simons. And so you'll find that counting these things is the same thing so counting solutions here is the same thing as counting, it gives the Chern-Simons partition function. So that is somehow just plus, so this thing plus string field theory. invariant for term silence is in fact equal to this string partition function. I think maybe this it's coefficient. So, right. So then, so this is somehow, no, I think this paper is from 92 or something like that, and then a few years passes, and then if one looks at this partition function again, so now some ideal buffer enters the story, and if you look at this partition function, you can somehow, you can sum the holes, you can somehow take the holes out of the boundary components out of the story, and what you would get is something like n to the minus 2g f of that. Fg of that. And then this somehow, formally now we had some kind of string theory with boundaries that we summed up over the boundaries. So now this sort of looks like string theory without any boundaries in it. So it indicates that you should be able to kind of take these things out. And Buffer's suggestion is then to use what's called the conical transition. So at least I should say we now restrict to y equal to 3 sphere. So we're going to do this for the 3 sphere. And so let me and collapse and perform. In what's called conifold transition. So, in the interest of time, I think I'm going to. Just briefly, we're working initially in P star S3, and we are relating the theory in this P star S3 to something in the following manifold. So we take two minus 1 bundles over P1. So this is also Calabian. In fact, at infinity, it looks exactly like the T star S3. So in formulas, it's just a matter of taking this. So again, I can also get to this. So you take the sum of 4 squares and set it equal to a real number, and that's a model for this. And when you crash this into 0, you get a singular surface, which you can look at as a cone on S3 times S2, and then you resolve it. So let me just draw that picture. So what you have somehow is a space that looks like this. So this is maybe S2, and this is S3, and you have this conical singularity when you crash the 0 section to 0. So you put this conic, it's the singular conic. Now you have two ways of resolving this. So one way is that you expand the S3, so it starts looking like this. This is S3. And the other way is that you expand the S2 space, so it starts looking like this. And what Buffer's now saying is that if you take, so secretly I didn't say very much about that, but these gauge indices, you can think about taking n copies of the 0 section. And then this open string theory over here should correspond to the closed string theory over here, where the area of the P1 in the middle, so this is the symplectic manifold, and this is a holomorphic P1, we can decide what its area should be, and where this is equal to I times lambda. So this is what's called this folder transition, and it predicts that, in fact, the Chern-Simons should be equal to the. So again, we have now a closed topological string theory, and in the same argument that I gave before, you can see this one localizes on the moduli space. So this is nothing other than Ron-Whitney theory here. And that can be computed. So you can somehow just, if you're simple-minded, you see there's only one holomorphic sphere here, but you have all the multiple covers, so you have to somehow do some virtual perturbation, and that gives you such perturbation expansion, and it agrees with what's not expressed. So it's a somehow powerful test. Okay, so to continue the story, there's one more ingredient that has to be added, and that's what happens when you have knobs. So far we get somehow Chern-Simons on a free manifold, but when you have a knob K inside, let's say S3, then you can take maybe I should put N, SUN. The expectation value of the corresponding Wilson loop, so that means that you're basically taking this pattern together again, and then you take the same thing as before, where you have a connection, but here you insert the trace of the holonomy of connection A around K. And so you try to do the same integration, and it's somehow so celebrated, taken by Whitney, he proved that if you do this for SU2, then in S3 you get the Jones problem, somehow proved in some sense. Okay. Yes?
Second, when you perform the manifold transition, what changes in what corresponds to what?
So the idea is that the open string theory on T star S3 with value in S3 and any copies of S3, so we have some of these aggregation indices, corresponds to the closed string theory in the conifold with resolved conifold maybe it's called, with this particular value for the area of P1, which enters into perturbation. And this can somehow be verified with this level, just computing it in different ways. Okay, so the main question now, and so here you should think about something like conflict polynomial, but now one wonders what's the counterpart of this on the other side. So there should be something. So we're now on this side, right? Doing that, and then we should sort of try to transfer it to the other side, and that should be the following, that we can somehow relate, maybe again, I won't be precise, but one can write some precise statement in terms of, again, in terms of path integral, but one should relate, so I'm just saying relate this. So, open strings on a Lagrangian L in the conifold, in the resolve X, which looks like lambda K and K. So that's somehow one should now, in order to express this in some sort of symplectic way, again, this in symplectic terms, this is some statement about many years ago that this was somehow predicted, but now there was somehow real contact made, and that was by them invoking mirror symmetry somehow. And so I'd like to put this in quotes because it's clear that not everything here is understood, but what they're cooking from this perspective, and unfortunately I don't have time to say exactly how, because I want to do some geometry at the end, so that's why I'm sort of a bit stressed out. But anyway, so they find, so they associate to which node? Okay, a polynomial which I call A, maybe I should call it A, but I don't call it A. And then on 3 variables, so this is our lambda, this is our mu, and then they put it. I'm going to write Q because I'm sorry about that. But this is somehow, they want to make clear that this is a broken variable. So they write it like that, such that A into the x into the p q is equal to uv. So these are 3 variables, and we should think about q as fixed, somehow, some fixed numeric value. And so we have 2 variables and 2 other variables. So when we take the 0 locus of this thing, we get the three-dimensional manifold, which is some sort of family of cones over the curve, right? And that manifold, so this locus is, so this is what are you is, what was it? U and V are now additional variables just thrown in. And so I should say that this, but let me not try to make it precise. But this manifold, for any k, so is a mirror of x. So that was just the solved manifold. And we need to have so in mirror symmetry, you can somehow either do things in the A modulus sketch here, kind of homomorphic curves, or you can do things with weird shapes over on the B side, and then now we're just going to go to the B side, and this is the mirror. So for any node k, we sort of predict that this is the mirror of the conifold, so it's independent, but and somehow the locus inside here, given by b equals 0, is mirror to the Lagrangian brane F. So in some sense, what should be the case is that you can now compute everything that came from this open string theory, but you can compute in terms of this study sheets of this algebraic right? And so then they have some description of this A, which is not maybe 100% clear how they get. They of course know, but it's not on the level that if you're given a node, you just can find this A. It's involved and so on, but in all examples, which is made out of few, AK is the augmentation for the node. After possibly this change in variables. And this is somewhere where this what conjecture that Lenny mentioned at least is coming from. So the point is that on this B side they can somehow add some U1 action in the theory. We have to find it somehow, and that would add an extra better number to things, and that would conjecturally be the homology of object. So to say, to make kind of some short prediction, and classical curve, the zero set knows everything. So the prediction would be that if the augmentation polynomial of k is equal to the augmentation polynomial of k prime, then somehow this, I don't know how to make this sort of Covalent homology of any as that thing, okay, is equal to the covalent homology. So this is as for the invariance as always. So this is prediction. Okay. And then of course a lot of questions arise, and in particular how to make contact between these theories, and so we like to see some sort of traces of this non-mobility potential in the Sondrian DGA of a knot. So let me start out by saying somehow completely describe this classical. So now back to this T star S3 or R3 or whatever we are. So and that's now so this too long, but anyway, let's go back to Lenny's lectures where he described this DGA of the Sondrian common lift of a knot. So if this is so if an exact Lagrangian L with T star S3 induces with boundary such that the boundary is boundary at infinity of L is equal to lambda k. So this is lambda k is reduced this notation. So this is the conal torus of the k induces an augmentation of the algebra of k. And the proof is somehow easy. So we have a geometric definition of this map. So in the picture you should have in mind is that so we have this. Here is lambda k, and here somehow stretches in this L. And now what we can do is we can define this map, let's call it epsilon, from the algebra into, actually we can take it into the grouping of the homology. So the homology of S3 and L, I guess. So how do we do that? Well, we just counting. Here is a vector A, and then we somehow count holomorphic disks. I don't know, something went wrong, but we're counting holomorphic disks with boundary on L, and we count them with coefficients here. So that's a map into here, and we need to check. We extend it as an algebra map, and we need to check it's a chain map. So the chain map here just means that epsilon compose d plus d compose epsilon, where we can notice when the trivial differentials of this goes should be equal 0. But that's somehow by this SFT compactness theorem obvious. So we need to look at boundaries, these one-dimensional moduli spaces, and we know that it will split up into something of the following sort, where these are rigid disks in the interior, and this is a dimensional one. This is actually being composed with epsilon sigma. So that's fine, and let's take a look at what kind of Lagrangian, exact Lagrangian fillings we have. Well, there are two obvious ones. So one is the cone model. So the Lagrangian cone model. So we have the cone model torus, but we can fill the fibers. And then what's the augmentation? Well, the augmentation is mu is sent to 1. So that the meridian is homologous to 0, right? And second, we have the complement of the knot. So that's S3 minus K. You can see that, you know, picking it's not very deep. So if you do the same thing in T star S1, then this would be the knot, and you can certainly pick something like that and be exact. You can just go out and find it and go. Let's see if I can get to the details. But from homological point of view, this is just killing the meridian. So the map here is lambda over 1. So these two fillings show exactly this thing. Then you mentioned that 1 minus mu, I mean, there's a sign confusion probably, but 1 minus mu and 1 minus lambda divides the augmentation by 1. Okay. Here, maybe I'll skip something because I want to get to the main correction. So now, this is nice, and one can look, if one looks sort of more attentively at augmentations induced by looking at holomorphic disks on the complement, one can actually recover the chord algebra. So somehow, instead of mapping into H1, you can map into grouping of the fundamental group of the complement, and you can check that the image somehow is the chord algebra. So in fact, the augmentations mapping into the complement are much stronger than just doing this little thing. It actually encodes the entire H0 in some sense. But now let's take a look at somehow the main new equation. So this somehow is appearing in many ways, and this appeared before, but here is somehow like a new ingredient. So now one can using we want one can shift these two. So maybe I call the Ekholm I call it LK, and the complement I call it MK. One can shift LK and MK minus points, at least, off of the 0 section, making them non-exact. But that means that now we can shift them off, and then when they're off, we can perform the coniform transition. So we have the Lagrangians bounding the knot at infinity inside X. So we can do LK, MK, as some manifolds of X, Lagrangians of manifolds, and they have the right asymptotes. So now, let's take a look at how the picture changes. So what can we do with augmentation? So we'd like to kind of do the same thing as we did before, but it won't work exactly as nicely. So now we try to define augmentations in the same way. So in other words, we have the same picture. We have here somehow here we have lambda k, and here we have LK and MK, let's say LK. And then we try to count disks going like that, and then we try to kind of to make a chain map out of it. Well, you see, there is a somehow well-known and well-studied, say by people like Fukaya, boundary bubbling that prevents this. So we look again at boundaries sort of one-dimensional moduli spaces, and the sort of the good splitting, as we saw before, it was this one. So that these things somehow, here is epsilon, and here is d, so this would say if all value looks like this, it will be epsilon equals d 0. But now they don't, because there could be also splittings of rigid disks forming inside the boundary on this LK. Maybe there is such a rigid disk here, and it would somehow, in one parameter family, split off. But these rigid disks, so now if you think back, that we're in this manifold, and it's easily checked, it is LK, and LK has a mass of 0, and the Chern class of the manifold is 0. So in fact, all such disks are rigid, and they're exactly what corresponds to the Gromov-Witten potential, what contributes to the Gromov-Witten potential of LK and LK. So if somehow we could account for this problem, then we could somehow get new augmentations, possibly slightly different. But this problem has to be known since long, and one can somehow find a solution, and we can introduce obstruction chains. So if you do that, then you somehow fix for each rigid disk, you fix a homology going to infinity, where we express it in terms of homology variables p and x. So for each curve, we take some sort of, it's up we take some surface going up to a generator of the homology upstairs, into a combination. And so now, what we should count is, rather than counting these things, we should actually count things that become rigid after we hit this yellow thing. And so then, and we should count all such configurations. So it's somehow problematic count, perhaps it's a very big one, but if we do so, then at least we get the chain map. Provided one thing happens. So let's take a look at what should happen. So we have this curve, and what we see is somehow this yellow piece, or whatever the color is, it could hit here, or it could hit here. So that means that in order for this to be a chain map, we define epsilon by counting such configurations. But to define, we need also to redefine delta, because delta, I mean, here we have a splitting which is not visible in the usual delta. But that's not so terribly hard, so we're in the torus, and basically we have to take this curve, and each time we intersect this reference chain, we need to kind of count something, and that's easily done, because it's just about looking at the homotopic or homology class of this and intersecting with the do. So, in other words, just to say something definite is that if we change, so change variables in the coefficient ring, and set x equals to x minus dw and capital P equals P minus dw dx, then, and that's somehow just, I'm going to wrap this up in 1 minute, but let's somehow just understand what's happening. We need to say what is W. So WXP is the somehow this Gromov-Witten potential, so it's some number which don't integer, but so it's counting the number of curves in this homology class, and now, so perhaps in some cases all these homology classes are 0, but now if we do this change of variables, then the new differential would give a chain map into the kind of homology, sort of quantum homology, if you wish, of the field. And so the basic, so for example, the basic augmentations correspond to x equals 0 or p equals 0. Right? That's when we fill the cycle and do nothing more. So in our original variables, this means that we find that x is equal to dw dp, for example, or if you wish, each of the x equals to each of the dw dp. So you see that this thing that I've written here is now actually a branch of the augmentation variety. And this is exactly as predicted by looking at somehow perturbation expansion of what these physicists are doing. So just, I'm going to stop in 1 minute, so let me just say a few more words. So this is some of the basic construction. More things came out of this, so there was somehow some question as to what happens if you take a link instead of a knot. So if you take a link instead of a knot, then you have augmentation coming from the individual pieces. Right? So basically say that you take a conormal filling on each one of them, there will be an augmentation. But there are also augmentations that augments mixed chords, so perhaps chords going from one component to another non-trivial. And therefore one can define augmentations that are induced by the complement of the link. And looking at the polynomials and some other predictions from physics, the corresponding augmentation variety, say for fixed Q, should be a Lagrangian variety in the space of xp. So now we have 7x and 7p variables. And in the space where you can take this exactly from the xdp, it should be Lagrangian. And moreover, you should get the n-1 component augmentation variety, which is n-1 dimension, should be, by Lagrangian reduction of one of the components. And this can actually be verified plain in the potential and a specific value for these complements. And that's somehow almost where we stand. One can actually also say that just as in the classical case, where one can map into the chord algebra, one can do this for these Lagrangians as well, in particular for the components, and one would get some sort of image which would be the Q deformation of the chord algebra. And that's not so much about it, but at least one can check that for those augmentations that come from some representation in this chord before chord algebra, all these properties of Lagrangian intersections and it seems to hold. So that's basically the same argument as for the trivial representation carry this map. So that's maybe where it stands. So I should stop.
Questions about Tobias's intriguing lecture on physics?
Can you elaborate on that last statement?
On which statement?
The representation.
Right. So if you have such representations, or whatever it is, right? So you have an n component here, so K1. Okay. So then you can look at the augmentations that are induced by taking this filling that now has many ends, right? And then you can count these curves going down. And you compose that or you can look at this as augmentation into this, right? In some sense. And for those augmentations, you can check that the corresponding augmentation variety is Lagrangian. And moreover, if you look at so you have now this chord algebra for this and the chord algebra for that, and if you look at some representations which agree on the last component, then those are what allows you to do this Lagrangian reduction, and the a piece of this sort of n-1 coordinate is given by that reduction. So unfortunately, we cannot prove these things. We don't know that all connotations come from here. Good conjecture, but we don't know that. And it seems that probably what one should look for is some generalization of Benny's. Well, the first one would actually dream of actually computing this. It's not impossible. Probably. I mean, combinatorial. But maybe, other than that, one could also see that if you have one of these GLN things, then actually it also will introduce something here. That you could maybe know without computing. And that's somehow in line with what it should be.
More questions? If not, let's thank Tobias again.